All right, we're continuing with we did polyprotic acid like sulfuric acid. We're going to do bases next. Bases would be like a monobasic base. A monobasic base would be like A minus. A minus is going to react with water. In this case, it forms HA plus hydroxide. And so acids, when acids hydrolyze water, they form hydronium. When bases form, hydrolyze water, they form hydroxide. And we call this KB. B is for base hydrolysis. It's just base plus water. The bigger the KB, the stronger the base. Or PKB, if you want to use our function. And then we have polybasic bases. You know. So for example, like a dibasic base. A dibasic base would maybe just have a 2- charge. And so for a dibasic base, we're going to have a KB1 and a KB2. We'll go through an example of that. A tribasic base is about the most we're going to get, A3-. This will have a KB1, a KB2, and a KB3. So let's take a look at, like, it doesn't have to be, you know, the charge here, it doesn't have to be negative. It can also be neutral if we're dealing with an amine. And so let's take a look at an example here where it's a neutral. The example would be something like ammonia, NH3. If we look at NH3, then the equation is NH3 is neutral itself, but it's H2O liquid. This is going to produce what? Let's produce here. Ammonium ion and hydroxide ion. I have my stand here. Over here. Ammonium and hydroxide. Now the KB for this we can look up. It's 1.8 times 10 to the -5. -5, it's fairly weak base. And this just so happens to be, you know, the Ka for acetic acid is 1.8 times 10 to the -5. It just happens to round to the same number. There's no other connection between acetic acid and this. And so 1.8 times 10 to the -5, and this is going to equal the ammonium concentration times the hydroxide ion concentration divided by the ammonia concentration. Typically, when we're dealing with Kb, we get the POH. And so the POH is just equal to the negative log of the hydroxide ion concentration. And then eventually, I mean, we have to figure out the total because this is going to be the total hydroxide. And so we're going to get hydroxide from the base itself plus hydroxide from what?
Ionization.
Yeah, autoionization of water. And then we can calculate the pH. The pH is just 14.00 minus the POH. So we can figure out the pH. pH should be greater than 7 for this. Manipulation. So let's go ahead and do a calculation for the ammonia. So, example here, we'll just do 0.100 molar ammonia. So, 0.100 molar ammonia solution. We have Kb and Kw. So Kb and Kw. Which one's going to be the greater hydroxide ion contributor to this solution? Well, we look at the magnitude of the K. So this is 10 to the -5, this is 10 to the -14. we're going to do this stepwise, and the greatest contributor to hydroxide would be Kb. All right, so let's do this. Now, for base solutions, we just look for the hydroxide ion contributors. For acid solutions, we look for the hydronium ion contributors. For acid solutions, look for hydronium ion contributors only, actually. For base solutions, we just look for hydroxide. Since water, Kw produces both, and we factored in for both of these. Look for hydroxide contributors. So we have two hydroxide ion contributors, it's ammonia and Kw. So we start off with ammonia. So step one will be Kb for ammonia. It will be NH3 plus H2O liquid. It's going to produce ammonia and hydroxide. Brand new pen. It's not so good. All right, so setting this up in our table, you know, the initial is 0.100 molar. Water is a liquid. Let's get rid of that. And then we're going to assume nothing's hydrolyzed yet. This is going to be change minus X molar plus X molar plus X molar. And so at equilibrium, we're going to have 0.100 minus X molar, X molar, and X molar. We plug this into the Kb expression over there. The ammonium concentration is X. The hydroxide ion concentration is X. So that gives us X squared on the top divided by 0.100 minus X on the bottom. Then we just try the simplifying assumption and see if it works. So it's X squared over 0.100, which means that X is equal to the square root of 1.8 times 10 to the minus 5. I end up ordering another one of these calculators. It's gone up in price last time I got this. But now they have the plus model for the Casio. And I get 4.24 times 10 to the minus 3. So when we calculate the change, the percent change here is going to be 0.004. So it's actually a 4.24% change. Is that acceptable? That's acceptable. I mean, it would be, you get a more accurate answer if you did the quadratic, but it's not necessary because it's still below 5%, and so we'll say it's acceptable. And so over here, this is going to be 0.00424 molar, 0.00424 molar, and then this is going to equal 0.995 99571. No, that's right, 76. What we say here is this is going to be 4.2% hydrolyzed, or you know, it's 4.2% reaction. What we have here. Oh, is that right? No, I made a mistake. Did I? 0.4. You got a different X?
Yeah.
What did you get for your X? 0.001336. Let me try that again. Actually, I got this. Anybody else?
I got what she got.
0.0.
1.3 times 10 to the negative.
1.3. Maybe my writing's bad. You took the square root of 1.8 times 10 to the minus 5?
1.8 times 10 to the negative 6, because you have to multiply it by 0.1.
Oh, right, by 0.1. Okay, sorry. That's right. what was it? 1 point,
1.3 times 10 to the negative
okay, give me one more digit.
1.33.
33, okay. And so the percent change is 1.33%. And that's going to change this. This will be 0.00133 molar, 0.00133 molar. And what's this one? 0.9877.
0.09, right?
Yeah, 0.09877.
I
What
got
were you?
6 right now.
6.
Because I got 1.34.
Yeah, okay, 6. Yeah. All right? Is that right? No? The 6 is not rounded. All right, let's double check this just to see. So it's going to be 0.00133 squared divided by 0.09866. We have 1.79 times 10 to the minus 5. So, and check the K out. It's 1.79 times 10 to the minus 5, which is good. But the pOH depends on the total hydroxide. Now, did we factor in the total hydroxide? No, we didn't. What else is going to contribute to the total hydroxide?
The autoionization of water.
Yeah, autoionization of water. How much will the autoionization of water contribute? The maximum amount it would contribute to hydroxide. And let's say if there were no, like in this case, the predator would be like the hydroxide. Let's say if there's no hydroxide, autoionization in, let's say, an open field with no predators around would give you 10 to the minus 7 molar hydroxide. But there's already a bunch of hydroxide present, and if there's already a bunch of hydroxide present, then the amount is going to be less than
0.7.
yeah, right. And so this is how you can tell. If we're only interested in pH, I would not continue. I would not continue because I'd look at the number here and say, you know, the most hydroxide I'd get is 10 to the minus 7 molar. Would 10 to the minus 7 molar make any difference here? No, it'd be negligible. And in fact, I'm going to get less than 10 to the minus 7 molar because of something called the common ion effect, which I just described using different words, but that's what we're dealing with. And so if you're ever uncertain, just go ahead and calculate it because it's better to be safe than to miss it. And so if we're going to see step 2, how much additional hydroxide we're going to get, let's go ahead and set that up. Step 2, I have the autoionization of water, H2O liquid plus H2O liquid. This is going to give me hydronium plus hydroxide. And so all this hydroxide from step 1 goes down here, and that's going to be 0.00133 molar. And we assume that water hasn't hydrolyzed yet. So we'll just set up our ice table here. And so we're going to get plus X molar plus X molar. And so at equilibrium, we're going to have X molar and 0.00133 plus X molar. And so there are different ways of visualizing this. One way of visualizing this is what I was saying. You know, if this were 0 and 0 and there was nothing around, then we would get 10 to the minus 7 molar. But since we have a lot of hydroxide, hydroxide is a predator for hydronium. So the hydronium population can't grow too big. Otherwise, the hydroxide will start attacking it and force the reverse reaction to occur. And so that means the population can't grow to, you know, its normal population, which would be 10 to the minus 7 molar. And so it's got to be a lot smaller. And the other way of understanding this is Kw. When we look at Kw, you know, Kw is going to equal the hydronium times the hydroxide. And so this has to equal the constant, 1.0 times 10 to the minus 14. And now, if I have x, rather than x times x, it's going to be this 0.00133 plus x, and so x can be a lot smaller now in order to satisfy this. Well, let's go ahead and calculate what that x is. So I just automatically, I'll just try the simplifying assumption. This is going to be x times 0.00133, which is equal to 1.0 times 10 minus 14. So let's calculate it. 1 times 10 minus 14 divided by 0.00133. And so I get an x value of 7.51 times 10 to the minus 12. 7.51 times 10 to the minus 12. Percent change is over 0.0013, so divided by 0.00133 or 33 times 100. You know, it's like a 5.6 times 10 to the minus 7% change, which says the simplifying assumption works fabulously here. In fact, the additional x that we generate is negligible compared. I mean, this is 10 to the minus 12. So the hydronium over here is going to be 7.51 times 10 to the minus 12 molar. Here. And then we started off with 0.00133, and then we got to add some additional hydronium to this. So it's going to be, I need 11 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros, and then a 7, 5, 1. And so let's see how many extra zeros I need. 1, 2, 3, 4, 5, 6 zeros. So it's going to be 0.00133, then 6 zeros, 1, 2, 3, 4, 5, 6, and then a 7, 5. And so when we look at the additional hydronium, is this, the 75 at the end. Was that significant? No, that was insignificant. So if we were interested in just in the POH, I would have stopped at step 1 because I know 10 to the minus 7, which is the biggest, won't have any impact. And in reality, it was 10 to the minus 12. We could do the same thing for acids. This is why in Chem 4, they just go ahead and ignore it, because even if you have a little bit of hydronium or a little bit of hydroxide, Kw isn't going to add much to that. Now, this is good because does this perturb the step 1? You know, this tiny addition here. No, the tiny addition does not perturb step 1. And so the advantage, we have to do all the steps for an inventory, but we don't have to do all the steps for pH calculation. If I was interested in the pH, I would have stopped at step 1, calculated my pOH based on this, and knowing that Kw is not going to contribute much, then figure out my pH from the pOH. If I'm interested in inventory, then I want to know all the species. So I have my ammonia here, the hydroxide here. The ammonium gets, oops, no. The ammonium stops here. Sorry, I shouldn't have cracked that out. The hydroxide goes into the next step. And so what do we have in solution here? Let's see if I have a decent pen. So if this beaker is labeled 100 molar ammonia, then the species that's present in the greatest concentration are ammonia molecules. And the ammonia molecules could be 0.09866 molar. Then I'll have some hydroxide. Hydroxide is 0.00133 molar. And then I'll have some ammonium. The ammonium stopped over here at 0.00133 molar. And then I'll have some hydronium. Hydronium is 7.51 minus 12. All right, to calculate the pOH, we'll take the negative log of the hydroxide. So let's take the negative log of 0.00133. So the pOH is equal to 2.87. So let's see, how many, I'm only allowed 2, so 2.876, which means the pH is equal to 11.123. Will be the pH here.
So in order to see with respect to compare step 1, you have to see if the hydroxide concentration is bigger than the previous one, or is it?
Yeah, if it changed significantly. This one changed, but was it changed significant? That is, if you plug this hydroxide over here and double check K again, did it change? No, it doesn't really change. We're okay. This whole thing goes for acids as well. You know, for acids, if you're only interested in the pH, oftentimes you can skip Kw, or you can even skip subsequent steps. Let's take a look here at, let's do phosphate. Do 0.100 molar phosphate. Like sodium phosphate. Actually, maybe I should do sodium phosphate, Na3PO4. I'll do Na3PO4 because I'll show a couple of things. Phosphate here. This is going to have a couple of additional steps here. You know, because phosphate is what we call a tribasic base. And so the biggest K is the soluble salts. Now, soluble salts are strong electrolytes. And strong electrolytes dissociate completely. And so maybe I'll call this like a step I here, where we have sodium phosphate in water. Say H2O like this. I'll put the H2 over the area. And this is going to give us 3 sodiums plus a phosphate. So we know it's soluble. So this is going to be sodium phosphate 8 cubed. So if we start off with 0.100 molar sodium phosphate, 0 here, 0 here, you know, I know K is going to be very large for this because it's a strong electrolyte since it's a soluble salt. So K is very large. That is, we expect this to be completely dissociated in solution, so we should have no intact units. And we're going to end up with 0.300 molar sodium ions, 0.100 molar phosphate. The sodium ions stop here, but the phosphates will continue on, because we know phosphate can hydrolyze water. So let's go over here. So this will be our step 1 here. And that's just going to be phosphate. Phosphate hydrolyzes water. Now, when we do water hydrolysis, we just do one at a time, one proton at a time. So this is going to make monohydrogen phosphate plus hydroxide. We call this Kb1 for phosphate. And Kb1 for phosphate is going to equal, you know, the monohydrogen phosphate concentration times the hydroxide ion concentration divided by the phosphate ion concentration. Kb1. And then we try to go look up Kb1 in a table. And try to look up Kb1 in a table. It's not there. So what do we do with this? We have to use a relationship, because if you look at that table there, are there any Kb's listed there? There are no Kb's listed there. And so there's a relationship. We call it the conjugate relationship. it turns out that Ka times Kb is equal to Kw. These are for conjugate pairs. We could do a quick, just a quick calculation to show that this holds. Like, if they're conjugate pairs, then the Ka is going to be the hydronium times the A minus divided by the HA concentration. That would be the Ka expression. The Kb expression is going to be the HA times the hydroxide divided by the A minus. This is for the generic. And so you can see the A minus is canceled, the HA cancels, and that leaves you with hydronium times hydroxide, which is Kw here. But they have to be conjugates, otherwise these things don't cancel. And so they must be conjugates. So that means that the Kb1, this is for phosphate, you know. Kb1 for phosphate is going to equal Kw divided by the Ka for its conjugate acid. What's the conjugate acid for phosphate? The conjugate acid for phosphate is monohydrogen phosphate. So we have to use the Ka value for monohydrogen phosphate. What is the Ka value for monohydrogen phosphate? And you know, the table up there is different than our book. We probably should use our book's value. Does somebody have the book handy? It would be in the polyprotic acids section. It's there. Well, monohydrogen phosphate here is 2.2 times 10 minus 13. Yeah. 4.2 times 10 minus 13. So this is 2.2 times 10 minus 13, but our book has a 4.2 times 10 minus 13. And so this would be 1.0 times 10 minus 14 over 4.2 times 10 minus 13, which gives us what for Kb1? Which is fairly big. It's fairly big. I mean, although that might not look so big, that is fairly big, which puts it kind of at the border between weak acid and strong acid. I mean, not weak acid and strong acid. It puts that at the border between a weak base and strong base. Actually, what is at the border of weak base and strong base on that chart? You see it? What's the strongest weak base on that chart? The strongest weak base on that chart is, what's the strongest base on the chart? How about that? Amide? Yeah, amide is the strongest base. And then what's the next strongest base? Hydroxide. And then?
Water.
No.
Oh, no, sorry.
Don't start jumping from side to side. You don't go amide. This is not hydroxide. You know what that is called? Oxide? Hydroxide. We don't jump to water over here, but actually sulfide is between here. Sulfide is actually stronger than hydroxide. Sulfide was misplaced. The K value is wrong. It should be down here. This is more recent K value. And then hydroxide is the border of the strong bases and the weak bases. So the strongest weak base is phosphate. Hydroxide is considered strong base, not a weak base. And so the strongest weak base is phosphate. And so this Kd value is actually kind of big because that puts it right up against the strong bases. And so phosphate, you know, if you have a sodium phosphate solution, it feels very slippery like sodium hydroxide. Have you ever felt a sodium hydroxide solution? Hydroxide, the solution feels very slippery. Phosphates, same thing. They feel very slippery, the solutions. And so, well, anyway, we could set up the table here. So we're going to carry this down. So this is going to go down here now. So we're going to lose some of this. So the initial water, we're going to say none of it's hydrolyzed. I'll just reset everything. So we're going to have 0.100 minus X. I think we could skip this. This is going to be X molar, X molar. It's a familiar pattern. And so this is going to be X times X, which is going to be X squared over 0.100 minus X. And then we use the simplifying assumption, the SA. X squared over 0.100. Which gives us what? So I have 0.0238 times 0.1. Try not to forget that. Then we'll take the square root of that answer. Square root of that answer. Just 0.0487. Ooh. Which gives us a percent change of what?
4.87.
48.7. 48.7% is not going to pass, right? Unfortunately, this is not gonna, this is a fail. Maybe you could have seen it's gonna fail because the K is kind of big, you know? And so the bigger the Kb, the more hydroxide. But even if you could kind of see it, you still try it nonetheless. I still tried it because, yeah, in the long run, it will save you time. Unfortunately, we have to get this in the quadratic form. So this is going to be x squared plus 0.0238x minus 0.00238 equal to 0. So let's plug that into the quadratic equation. Replay mode. We'll go to equation 5. And then the one quadratic, which is 3. And the A value is 1. B value is 0.0238. C value is negative 0.00238. It's been a while since I used that. So I got an X of 0.0383. That's my X1. My X2 is negative 0.0621. We can't have a negative polarity, so X2 is infinite. We're going to just go with that. We're only allowed for 2 sig figs, so we'll carry 1 extra. And so it was, you know, we figured it was a 48.7% hydrolysis. It's only a 38.3% hydrolysis. This is why I always pick 0.100 so we could do percentage calculations in our head. Because if you call that 100, then this is going to be minus 0.0383, which means we lost 38.3%, and we're going to be left with 61.7% remaining. Oops, but that's molarity here. So that's the phosphate. So we hydrolyze quite a bit of that. Over here, we're going to get 0.0383 molar, 0.0383 molar here. This is for the monohydrogen phosphate. This is for hydroxide here. All right, but this is a polybasic base. Since this is a polybasic base, there can be more hydroxide produced from Kb2. So we just did Kb1. Let's go on to Kb2 for this. And so what happens is with Kb2, that is now monohydrogen phosphate is also a base. We'll drop it down here. Down here. Both of these are going to go down to step 2. And so the phosphate doesn't drop down, so this is the end of the line for phosphate. And so we have monohydrogen phosphate here, HPO42 minus. And HPO42 minus can act as a base, you know, by hydrolyzing water. Hydrolyzed water form dihydrogen phosphate and hydroxide. And so we carry down the monohydrogen phosphate. So the initial monohydrogen phosphate is 0.0383 molar. The water is zero. Actually, water is nothing. We don't treat that. The dihydrogen, we assume none of it split up yet, and then the hydroxides from the previous step, 0.0383 molar. And so basically, we have some. From step 1, we have some monohydrogen phosphate, and from step 1, we have some hydroxide. All right. The change here, which way is the change going to go? Because now we have both reactant and product. The change has got to go to the right. This is a 0 there. Minus X plus X molar plus X molar. Now, do you expect the change to be very big or very small? We expect the change to be small. Why? Well, smaller than it normally would. The reason why I expect the change to be smaller, because if this were 0 here, I would expect a bigger change. But since I have quite a bit of hydroxide present there, I don't need to generate as much. This is called the common ion effect. You know, this whole thing about predator and prey. The common ion effect. When you have common ion present, we expect, and plus the Kb, you know, each successive Kb gets smaller. So Kb1 is bigger than Kb2, which is bigger than Kb3. And so the base power decreases. Phosphate was a decent base, but monohydrogen phosphate is not going to be such a great base. Let's look at Kb2. This is Kb2 for phosphate. Kb2 for phosphate is equal to Kb for monohydrogen phosphate. Kb for monohydrogen phosphate is equal to Kw divided by the Ka for its conjugate acid. What is the conjugate acid of monohydrogen phosphate? H2PO4 minus. And so Kw is 1.0 times 10 to the minus 14. What is dihydrogen phosphate? Well, dihydrogen phosphate on this chart here shows the value of 6.23 times 10 to the minus 8. Sorry. Let me see your chart again. Do you know about online tutoring? There's online tutoring available for Chem 1B through NetTutor. The school has a site license for NetTutor. And then somebody didn't log out of the computer here. And I found out there's going to be a tutor for this class. I'm going to meet the tutor, Mesa tutor, for this class. I've never met her though. Yeah. Do you have the number?
6.3 times 10 to the negative 8.
6.3 times 10 to the negative 8. And for H3PO4, since you have your book out, what is the Ka for H3PO4?
7.1 times 10 to the negative 3.
All right, I'll write that over here. You don't have to ask me. All right, so we have 1 times 10 to the negative 14. Oops, I need to get out of this. Over here. 1 times 10 to the negative 14 divided by 6.3 times 10 to the negative 8. Which gives me a KB value of 1.58 times 10 to the 7 times 10 to the negative 7. Is that what you guys get?
Yes.
Yeah, okay. Well, that KB is quite a bit smaller. This KB is orders of magnitude, like 5 orders of magnitude smaller than the previous one. And so there are two things that are going to make this a very small addition. In fact, this might be so small that if I was interested in pH, I might not do this step. I might not do this step because the KB is small plus the common ion effect. In other words, this thing. But if I'm not ever sure, I'll do it. I mean, that's a 10 to the minus 7 molar KB. And so here, this is going to be 0.0383 minus x, 0.0383 plus x. Now, this is what we're going to have. The KB for this is going to equal the dihydrogen phosphate times the hydroxide divided by the H2O4. Was x times 0.0383 plus x divided by 0.0383 minus x. We'll try the simplifying assumption. If we use the simplifying assumption, then that is just the x times 0.0383 divided by 0.0383, which is just equal to x. Your book comes up with a pattern. I just did something. I just erased it. 7.1 times 10 minus 3. The book recognizes a pattern here, but the pattern fails sometimes. For the second step, x is equal to K2. Right? And so the book will say, oh, x is just equal to K2. You see that? Step 2. But this failed. This would have failed for sulfuric acid. It worked for wheat, but it doesn't always work. Also, here, okay, let's figure out the percent. So in other words, x is equal to 1.58 times 10 to the minus 7. And fail. 1.58 times 10 to the minus 7, which gives us percent change of what?
4.14 times 10 to the negative 4%.
Yeah, it's no problem with the simplifying assumption here. There's no problem with the simplifying assumption. There's going to be 0.0383. Okay, minus. Even though there's no problem with the simplifying assumption, we still do the calculation. 0.6 zeros on these. 1, 2, 3, 4, 5, 6, and then a 1, 5, 8. We'll add some extra zeros here. Do the subtraction, so this is going to be 2, 4, 8, 9, 9, 2, 8, 3. Did we, we started off with 383, we ended up with 329. Did we lose much? We barely lost anything. Over here, the x is 1.58 times 10 to the minus 7 for the dihydrogen phosphate. For the hydroxide, we have 0.0383 plus x, so plus 1, 2, 3, 4, 5, 6, 1, 5, 8. All right, if you look at the hydroxide, and oops, I didn't want to double box this. The hydroxide's not done yet. All right, what we have to do is we have to see, does step 2 perturb step 1? And so, from step 2, we have monohydrogen phosphate. Did it change much? No, it really didn't change. And from step 1, we had the hydroxide. It didn't change much either, right? In fact, I didn't really have to do this step if I wanted POH. Could have gotten it from step 1. So your book comes up with another pattern. And the other pattern is for polyprotic acids and bases. Step 1 is going to generate the most hydroxide. The subsequent steps, because of the common ion effect, are going to be negligible contributors. And so if you're only interested in pH, you usually just do step 1, but it can fail. And so the problem that I did where it failed was for sulfuric acid. For sulfuric acid, step 2 was a significant contributor. In sulfuric acid, you had about an additional 10, 11% hydronium from step 2. And so when you look at that pattern and you try to see, okay, is there something I could have seen that would tell me that it would have failed? And the thing you could have seen is the Ka2 value in sulfuric acid. What was the Ka2 value in sulfuric acid?
0.011.
0.011. 0.011 is what we call fairly large. In fact, when you look at sulfuric acid, Ka2 is for monohydrogen sulfate or bisulfate. Actually, it's right here. When you look at hydrogen sulfate ion, it's close to the border of weak acid, strong acid. And so for sure, for something like this, with a fairly large K, that's going to be significant. So, in other words, on a test, if they're only asking you for pH, how many of these steps are you going to do? So far we've done 1, 2, 3. 3 steps if you count step I, right? Step I you could have done in your head, too. Well, anyway, let's continue on here. And so, actually, this is a tribasic base. And so we just did KB2, there's still one more KB to do, right? But we know something about monohydrogen phosphate. What we should know about monohydrogen phosphate is that monohydrogen phosphate is actually amphoteric. An amphoteric species can collide with water to produce either hydronium or hydroxide. And so I'm going to do an aside over here. Monohydrogen phosphate is amphoteric, and amphoteric means the collisions can result in two different things. And so if I have hydrogen phosphate collide with water, two things might result depending on the collision that happens. One is I can form hydronium and phosphate. This is called a Ka collision, as I generate hydronium. Or two, I could generate dihydrogen phosphate and hydroxide. This is a Kb collision. Can I say, okay, I don't want any Ka collisions to occur. Is that possible? I'm going to turn off the amphoteric nature of monohydrogen phosphate, and I'm going to tell it just to behave as a base. Is that possible? No, these collisions are just random collisions. You know, you can't control how they collide, can you? You can't, and so both collisions are going to occur. Are both collisions equally favorable? In water, they are equally favorable. But here, they might not be, because, you know, the Ka, what was the Ka for monohydrogen phosphate again? The Kb for monohydrogen phosphate, have we calculated that? Yeah, we did. The Kb was 1.58 times 10 to the negative 7. And so it looks like the Kb's favored. It looks like it, you know, if Kb's favored, maybe it's a base. So one's 10 to the negative 7, the other's 10 to the negative 8. Can we just turn off the 10 to the negative 8 collisions and say, no, you can't happen, right? Yes? No? No, and so what we should do is, shouldn't we do a Ka, that means? Are we forgetting to do the Ka? Well, we haven't even gotten there yet. Shouldn't I account for the Ka collisions? That is HPO4 2- plus H2O liquid is going to give me hydronium plus phosphate. I'm going to call this step 2B. So, you know, what I just did was, I just did the Kb collisions here. But what I'm going to do is I'm going to do this step 2B, which is the Ka collisions. Maybe I should have called it step 2A. And so what I'm going to do is I'm going to carry these down here. So I have some monohydrogen phosphate, 0.038299. And then water's out there. Hydronium, I have nothing. And phosphate, do I have any phosphate in here? No.
Yeah. What about that 61.7 remaining from step 1?
Oh, do I?
Yeah, you have 0.0617 more.
Oh, you're right. I did have phosphate. How much is it?
0.0617.
0.0617. Thank you. 0.0617. This is all the way from step 1. This is from step 2. And so, which direction is the change going? To the right. So this is going to be minus x molar, plus x molar, plus x molar. So at equilibrium, I'm going to have 0.038299 minus x molar, and 0.0617 plus x. And so this would take care of the Ka collision because it's amphoteric. Does that make sense? But take a look at this equilibrium here and compare this equilibrium to step 1. Compare to step 1. What do they have in common, and what's different about them? So just compare those two carefully.
As far as the equation goes, I don't know. Just like the fact that they both have meaning phosphate on them.
Yeah.
So we were taking away.
Yeah.
How we're adding.
Yeah.
We're adding more, yeah. To this.
So it's like because of step 1, it was a complete dissolution.
No, we're doing more, we're using more here, we're gaining more, that's the reverse. Yeah. Yeah, and then the reverse.
All right, so did somebody notice? What's the same about them?
About the Ka equation.
No, just the equilibrium line, the E.
So we're doing the opposite of what we're doing, step 1.
Yeah. It's kind of the opposite, but it's kind of the same.
Oh, it's still, it's like the reverse reaction.
Yeah, the reverse reaction. Except this is the way I see it. Step 2b describes the equilibrium between monohydrogen and phosphate. Step 1 describes the equilibrium between phosphate and monohydrogen phosphate. So they both describe the equilibrium between phosphate and monohydrogen phosphate, but in step 1 it describes it in terms of hydroxide. In step 2b it describes it in terms of hydronium. Hydronium and hydroxide are connected by the seesaw relationship called Kw. And so, do you know what? Step 2b is what we call redundant. We already did it. The only thing is we get pH instead of the POH. That's the only thing, and pH and POH are already tied together. And so this is redundant. Step 1 already describes the same equilibrium.
So we could call step 1 to say hydrolysis.
Step 1 is KB. Step 1 describes the same equilibrium as 2B. Therefore, let me give you a general rule for ice calculations. For acid solutions, Ka only plus Kw. So if you're dealing with an acid, even if you have amphoteric species present, and it can either collide Ka or Kb, you only consider the Ka collision. So the Kb collision, if you consider that, that would actually be a redundant calculation because you'd already have the. So for base solutions, we do Kb only plus Kw. This is a base solution. I would have never gone to Ka. I would have never done a Ka calculation because it's a base solution. And Ka is going to be a repeat of something we've already done, if we try to do it. Just like if I try to do it here, because I know monohydrogen phosphate occurs on both sides of that chart, it's both an acid and a base. I completely ignore its acid collisions because this is a base solution. It's a base solution. I only do Kb because if I do the acid collision here, we've already accounted for it. And so this is important because there are a lot of equilibria going on here. It can get confusing.
Just to be clear, we've already examined the acid equilibria, although not directly, by looking at how it reacts with water, like the ionization of water. Is that what you're saying?
Well, what I'm saying is we've already done this equilibrium. If we're doing this ice table, it's a waste of time because we already did this equilibrium. Yeah, in step 1, it's the equilibrium between these two species. It doesn't matter if we do it in terms of hydronium or hydroxide, because if we get hydronium, then the hydroxide we calculate using Kw. If we get hydroxide, we calculate the hydronium using Kw. They're tied together by Kw. So if the hydronium goes up, the hydroxide goes down, and vice versa. And so this is describing the exact same equilibrium that we had in step 1. And so we do it. We don't have to worry about doing that. And so that brings us to step KB3. Let's take a look at KB3 next, which we'll call step 3. Step 3, which is going to be KB3, is going to be, we're going to take the dihydrogen phosphate now and hydrolyze water. The dihydrogen phosphate can hydrolyze water in 2 ways. It can do a Ka collision to form hydronium, or it can do a Kb collision to form hydroxide. Now, those aren't redundant, right? Those aren't redundant here. I mean, it can do both collisions. But we're only going to consider which one. Even though this can be an acid too, we're only going to do the base because we're in a base solution. And so this is going to form phosphoric acid plus hydroxide. We drop it down here. The initial is going to come from the previous step, step 2. How much dihydrogen phosphate do we end up with? And how much hydroxide from the previous step?
0.083.
That's a little higher. Oh, well, actually, I better write the whole thing and I'm going to add some more. 0.0383.
00158.
All right, the change has got to be to the right, so this is going to be minus, this is going to be plus, and this is going to be plus here. So the equilibrium is going to have 1.58 times 10 minus 7 minus x. this is Kb3 for phosphate. The Kb3 for phosphate is equal to Kb for dihydrogen phosphate, which is equal to Kw over Ka for the conjugate acid. What is the conjugate acid for dihydrogen phosphate? Phosphoric acid. So this is 1.0 times 10 to the minus 14 divided by 7.1 times 10 to the minus 3. Oh, dude. 1 times 10 to the negative 14 divided by 7.1. 10 to the negative 3. 1.40 times 10 to the negative 12. So it's quite small. Kb. It's quite small, and I already have a lot of common ions. Therefore, I don't expect X to be very big. And so this is going to equal the phosphoric acid concentration times the hydroxide ion concentration divided by the dihydrogen phosphate concentration. It's going to equal X times 0.0383 plus X divided by 1.58 times 10 to the negative 7 minus X. Let's try the simplifying assumption here. So I'm going to just get X times 0.0383 divided by 1.58 minus 7. We have 5.81 times 10 to the negative 18. Now the percent change, I would want to do the biggest percent change here. The biggest percent change would be X relative to 10 to the minus 7. So we have 10 to the minus 18 is a change over 10 to the minus 7 is the initial times 10 squared. This is 10 to the minus 11, which is 10 to the minus 9%. It's no problem. So the dihydrogen phosphate is going to be 1.58. Actually, let's get this in decimal form. It will be easier that way. Let's go 6 zeros. One. All right, we'll do 4, 5, 6, 1, 5, 8. And then this is going to have 17 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 5, 8, 1. Did we lose much here? You think that's not even really going to register, is it?
No.
We barely lost any. Then over here, did we gain much? Yes. Even though that's an exceedingly small number, it's still significant. 5.81 times 10 to the minus 18. And over here, the hydroxide is going to be 0.038300158 plus 17 zeros. 3, 6, 9, 12, 18, 16, we gain much there? And so that's good, it doesn't really perturb anything. But anyway, we'll continue here. There's one more hydroxide ion contributor in the solution. What is it? Water. So let's go and find water. Why am I doing this? If I was interested in the pH, you know, would step 3 have changed anything? No, not at all. But just for completeness, step 4. We're going in sequence here because do you see step 3 was 10 to the minus 12. And step 4 is going to have the smallest K value, which is 10 to the minus 14. We should go in order, you know. It doesn't always have to go in order. You know, there are some bases, for example, like sulfide. Sulfide is a dibasic base. It's S2 minus. KB1 is the biggest. The next biggest is not KB2. The next biggest turns out to be KW. So it's a weird sequence. Step 1 is KB1, step 2 is KW, and step 3 is KB2. So we go in order of decreasing K values.
So is the first step always gonna have the most?
Yes. First step always has the most, because it always has the biggest K value. And so here, for H2O liquid plus H2O liquid, it's going to give us hydronium plus hydroxide, KW. Here, water. Initial hydronium is 0 molar. Initial hydroxide is the 0.0383. Dot, dot, dot. And then change, and then equilibrium. Equilibrium is going to be X molar here, 0.0383, dot, 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 plus X molar. That's going to be KW. We already know KW is hydronium times hydroxide, so because X times 0.0383 plus X. The hydronium times the hydroxide. Simplifying assumption here should work, no problem. So let's see. We have a lot of common ion here. What's the most? Hydroxide will generate from KW. If the fields are empty and there are no predators around, we would get
1.0 times 10 to the negative 7.
we get 10 to the minus 7 molar, but now there's lots of hydroxide around, which means the population can't grow as big. This is called the common ion effect. Population can't grow as big, the amount of ions we're going to generate is going to be a lot smaller. And so it should be a lot smaller than 10 to the minus 7 molar. Well, will 10 to the minus 7 molar make any impact on this? No, and so the but it will make an impact on the hydronium. And so let's see what happens with hydronium. And so this is, we already know what this is equal to. It's equal to 1 times 10 to the minus 14. So 1 times 10 to the minus 14 divided by 0.0383. I'm going to put in all the numbers here. 00158. I'm not going to put in 55. Well, maybe I should. I don't need to know if my calculator will take it. How many more zeros is that? 3, 6, 8. 8 zeros and a 581. So I'm going to try to plug it in. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it did. And then a 581. And so again, X value of 2.61 times 10 to the negative 13. 2.61 times 10 to the negative 13, the percent change is minimal. 10 to the minus 13 change over 10 to the minus 2 original times 10 to the minus 2 gives me about a 10 to the minus 13% change, which is no problem. It is. And so that means the hydronium is going to be 2.61 times 10 to the minus 13. More. I forgot to do something all this time. 0.0383, 0.015, dot, dot, dot. You know, one thing that I forgot to change, check. What did I forget to check? Yeah, I forgot to check double check the K values, starting with step 1. If I made a mistake on step 1, I'm screwed because I just wasted all that time on all the subsequent steps. And if I have a mistake on step 1, I really blew it because I'd have to go back and redo everything. Whereas if I had caught the mistake on step 1, then I would have been okay because I wouldn't have wasted so much time on the subsequent steps. So we'll just keep the fingers crossed, and can you go, well, let's just double check this one just to see. Actually, no, we should go back to step 1 because if step 1 is wrong, then it doesn't matter if I double check this one or not. And so can you double check the K value on step 1 and see, is it okay? Yes, okay, lucky. Okay, go to step 2. Can you calculate the K value for step 2? Now, the hydroxide did change, but it was negligible, right?
Yes.
So,
That one passes as well.
that one, okay. Did step 2 perturb step 1? No? Okay, go to step 3. Can you check that one for me?
That one passes as well.
Good, and then step 4.
Yes.
All right, so we're good then. We're lucky. Nothing perturbed the other steps. And so we could do this stepwise. Stepwise succeeded. And so what we do is we'll take the inventory. The sodium ions, 0.300 molar. And then the phosphate came out to what? Concentration for the phosphate. You have to follow it down to the end of the line. Phosphate ends at step 1, right? And it came out to
0.0617.
okay, then what's next? The hydroxide. The hydroxide, 0.0383 molar. And then the monohydrogen phosphate. What is the monohydrogen phosphate, the total concentration? We form some in step 1, and then we consume some in step 2, leaving us with how much total monohydrogen phosphate at the end?
0.03829.
0.03829. And then the dihydrogen phosphate.
1.58 times 10 to the negative 7.
And then the phosphoric acid.
5.81 times 10 to the negative 18.
And then the hydronium.
2.61 times 10 to the negative 13.
That should be the inventory for this. Now the pH we can calculate either from the hydronium or from the hydroxide. Normally for a basic solution, we just do the POH. And then convert that into pH. And so I'm just going to do the negative log of 0.033. That should be enough. Or I might go 0.01. 0.003. 0.015. 1.416. Which means the pH is 12.583. fairly basic.
Okay, where would you have stopped in this particular one? For if you were just asked for the pH,
What step, we could have stopped at step 1. Most of the time, you're okay with stopping at step 1. Because look at the KB value for step 2. The KB value was 10 to the minus 7, which is small. The only exception is, flip back to sulfuric acid. The only exception is in step 2 there. Take a look at sulfuric acid. We had significant additional hydronium generated in step 2. And the reason for that is because of the K value in step 2. What was the K value again for step 2? 0.011. Now that doesn't seem so big, but that's big. And so what we'd say is that's a significant contributor. And so if you look at your step 2 and you see a K value that's fairly big, then you better factor that in. But if you see a K value that's fairly small, like 10 to the minus 7, 10 to the minus 5 even, then we don't really factor that in. These are the main calculations. I mean, there are just a couple of little points I need to talk about in chapter 16 before we move on, but this is essentially it for chapter 16. So we'll start chapter 17 next time, but a couple of points I need to talk about, remaining points in chapter 16. All right, that's it.
The whole time that we were solving it, we used